so far we have worked on solids, we have worked on solutions, okay, with the concentration and all. Now we are going to gases, and I have not talked about gases at all, right? Okay, perfect. So then we're starting right from the beginning. So here in gases, gases are particles that are really far away from each other. So you know about solids. In solids, the particles are close to each other, okay, very close. So you can actually shape them into whatever shape you want. And then with liquids, the particles get a little farther away. Okay, and with liquids, they tend to shape the shape of the container. Okay, so whatever container you place them in, that's what it will look like. And then with gases, you really have particles that are far away from each other. Okay, and so which means that there's a lot of empty space over here, right? Okay, but there's nothing you can do about it. Okay, there's a lot of empty space. So right now, if you're sitting in this room and you're thinking about, you know, how much gas there is in this room, it would be how much? A lot. Okay, let's get a little bit more scientific than a lot. What would you say the volume of this room, what would we say the volume of the gas would be in this room? It would be equal to the volume of the room. Thank you very much, Zach. Okay, and so it would be equal to the volume of the room because it's the volume of the container. Okay, that's all it is. But is it accurate? No, because of all the space between gases. Okay, and so it's not an accurate volume, but we have to assume all of these things. Okay, and that's a huge assumption. Okay, that we have to make, that there is so much space in between gases. But if we don't do it, we can't work. Okay, and so that's why we have a whole chapter on gases, because they're very unusual. Okay, they do behave a little bit differently than liquids and solids. For the chapter 5, there is a self-study online. Okay, and I didn't print it out this time. I thought I'll let you guys print it out yourself. It's only one page. Please print that out and make a note. It's due on Thursday. Okay, not next week, this week, Thursday. It's very short. Okay, it talks about some of the theory of gases, some of the units for gases that you will need, because once you start dealing with gases, there is one new unit that you need that we did not talk about before, and that is pressure. We haven't dealt with pressure before because we didn't have to, okay? And the pressure comes essentially when we start dealing with gases. Pressure, as you know, is force per unit area. Okay, if you've ever taken physics, if you have not, it doesn't matter. I hope you have filled air in your tires. Have you done that ever? Yes? And how much air do you fill in there? PSI. That's what I was looking for. The units in there. And what do the PSI stand for? Pounds per square inch. That's the force per unit area. Okay, and so that's pounds per square inch. And that is the unit. But look at the unit we have there. Pounds. Is that SI? Inch? Totally not SIs, okay, that we're working with. But when you get to the pressure of gases, it is still the pressure, which means it's still the force per unit area, but we have a little bit different units, okay, for pressure. So that's also one of the things that you'll be working on that self-study. Okay, it's a very easy thing to do. Just look at all the different pressure units that we have, and also the conversion factor. So I have some conversions there for you also. Okay, so the three most common pressure units you'll be using are atmosphere, millimeters, Hg, and torr. Those three are the common ones, and then I'll have you, in that self-study, you have to look into what the SI units are and do some conversions for me, okay? That should be a piece of cake because that's so chapter 1, okay? And so you can do that conversion. The other thing I have there for you is a little bit about the kinetic molecular theory of gases, okay? The kinetic molecular theory of gases is exactly that, it's a theory, okay? And in the theory, you have to assume a few things, okay? Because gases are a little bit different, okay? And so you will find the kinetic molecular theory towards the end of the chapter, okay? It's not in the beginning. Usually these chapters, they do it at the end. I like to do it in the beginning, okay? The kinetic molecular theory, so that I have you do it before. And it's at the end of the chapter. It's also in the PowerPoint, okay? But it's over here. Please don't just copy all these things, okay? Like I had you do the Dalton's atomic theory. Don't just copy anything. Write it in your own words, okay? And I'll give you an example of what is covered in the kinetic molecular theory. So let's say you have all these gas molecules, okay, right over here. And these gas molecules, they're going to be moving around all the time, right? And how do you know they're moving, by the way? I told you they're moving, but how do I prove that gas particles are moving?
Because they're not solid, they're a gas.
So, but that's not the only thing. There has to be a way to prove it, right?
If it has pressure.
Hmm?
It has pressure.
So do liquids, and so do solids. They all exert pressure.
They're moving.
But how do we know that? That's what the question is. How do we know that they're moving? You can feel it sometimes, right? And you feel it in wind, for example. Okay, and that is because of the change in pressure. So you get the wind because of the change in pressure. Okay, that's one thing. And now in case, and I know we always get about, like lunchtime right now, and I always tend to mention food, but when you're making cookies, you can smell the cookies, right? Why would you be able to smell cookies? They're solid. You should not be able to smell cookies, but because there are some gas aroma molecules coming out of it, and because they can move, they come up to your nostrils, okay, and you can smell them, all right? And that's why we know that gas particles move. Actually, liquids also move. Solids move so slowly you can't see anything, okay, in there. But the liquid particles, they're also moving, okay? And if you've never done this experiment before, you can try this at home, okay? Just take a glass of water, transparent if possible, and just take a glass of water at night, okay? And then leave it on the sink, add a drop of food color to it, okay? Red, green, whichever one, and just leave it there, okay? And then come back in the morning and see what happens, okay? And you will see that the color is dispersed all over. Okay, and the only way the color can be dispersed all over the water is because particles are moving. Okay, if they were not moving, then the drop would just stay where it is. Okay, like in solids, you get stains on solids because the particles can only move so far because they move so slow. Okay, otherwise they would move farther away too. So anyhow, the aromas, okay, that is all gases. The whole perfume industry is based on this. Okay, on the fact that you can smell stuff, okay, and they have to be in vapor state for you to actually smell something. So in any case, when you have particles moving, okay, and coming back to the kinetic molecular theory, when you have particles moving, they're going to collide with each other, correct? Okay, and so let's get to collision, okay, of stuff. And so, and God forbid, if you ever see a car accident or if you're ever in any, but if you've seen Fast and Furious, you've seen car accidents, okay? And so when the car crashes, when the two cars crash with each other, what happens? Do they stop, or are they still slightly in motion and then they stop, or what happens? Do they stop? It's an easy answer. You watch movies, come on. Do they stop or do they just keep moving still? They stop, okay? And this is something that you learn in physics, is that the forces transfer, right? And therefore they come to a stop, which means that the force is gone. It's not there anymore, all right? One of the assumptions that we make in kinetic molecular theory with gases is that when two gas molecules collide, the energy between them is minimal transfer, and so they collide and they go right back into motion, okay? So which means there is no energy gain, no energy lost, okay? So it's a very big assumption that we are making. Okay, otherwise what would happen? If they were to collide and they were to stop moving, then we would have no motion anymore, correct? Okay, so this is an assumption that we are making, and that is kinetic molecular theory. So you'll find some more in there, okay? There are about 4 or 5 postulates in there. So that's the kinetic molecular theory. And then there are some properties of gases that you should know, which are different than the kinetic molecular theory. And one of the properties of gases, and they're all given in your chapter summary if you have them, already over here with you. So the first one I already mentioned, okay, is that gases fill up their containers completely. Okay, so there is no room left anywhere. The only room that is left is what you have displaced, okay, from the gas, but otherwise it's all occupied. And gases will occupy more space than liquids because of the more particles in there. By the way, gases, do you think they'll be less or more dense than liquids? Less. Okay, they should be less dense unless they're really heavy gases, at which point that they will sink. Okay, so the heavy gases that we have, very few of them, things like xenon, radon on the periodic table. Okay, those are the really heavy gases. But other than that, lighter gases, they will always have less density, okay, in there. Yes, George?
Something like a really dense gas like xenon, you put that in like a really light, less dense liquid, will the liquid just like rest on top of the...
It would.
Okay.
It would. And even now, actually, with radon, radon will travel underneath the earth. It never comes out. Okay, it does come out through pores, but it, you know, it mainly likes to be underneath the earth because it's so heavy. It can't come out so much. Okay, yeah. But yeah, that it would kind of strange visual, wouldn't it? Yeah, if you have just the liquid sitting there. Okay, and then finally, the third property of gas is that because of all this space in between the gas molecules, gases are compressible, okay, because you can push the molecules together and get rid of that extra space, okay. And so when you go and buy gas for, say, a picnic or something, and you need that little cylinder to take with you, that's all compressed gas, okay. But that's not an accurate volume of gas, is it? Or it is? It's not, because once you start using it, then you don't know how much is left in there, do you? Okay, but the container is still the same, okay? And in case you ever wondered why people don't use the fire extinguishers again, once you take out the pin, we say it's useless, right? You can't use that over again, in case you did not know that. That's the rule, okay? Is that once you take out the pin, you can't use that fire extinguisher again because, again, you don't know how much is left in it, okay? So it's actually a hazard then instead of a safety mechanism, okay, anymore. So once you start using gas, then the volume of that compressed gas in there is now inaccurate. Okay, it's not what you started with before. So it's different kind of things. Anyhow, so those are the properties of gases. So make sure you do that self-study. That will give you a whole idea of some of the other theories, okay, that are involving gases. Okay, so gases are a little unusual, and because of that, we also have some laws, okay, in gases. And the first one that I want to talk about is Boyle's law. And Boyle's law is the relationship between pressure and volume. Because we have all of these different aspects about gases, gases are really very sensitive, okay, very sensitive to temperature changes, pressure changes, volume changes, okay, because the particles are in motion, they are so far apart, so a little bit change will affect them, okay. So pressure and volume, how does this work? So let's look at a container. Here's a container, 1 liter, 1 atmosphere. And we're going to do something to the container. Before I do that, I need to ask you one more thing, okay, before I go too far into Boyle's law, is when we talk about pressure and we're talking about gases, how does those two relate? What does it mean when we say that a gas has pressure? How do we feel that? How do we explain that to somebody that this is why you're feeling the pressure? So how does the gas exert pressure? Yes?
Force
How?
divided by area.
No, but that is what pressure is. Okay, but how is it actually doing it practically?
Well, if the gases are bouncing off each other, wouldn't that cause pressure?
So, not with each other,
No, but on their container.
on the container walls. Is that what you were going to say, Jacqueline? Oh, no. Okay. All right. So, yes, with the container walls. Okay, that's what it is. So over here also, if this was in an enclosed space, all of this, that would be the pressure, okay? Not with each other. When they're colliding with each other, you don't feel the pressure, okay, at all. But as soon as they collide with the wall, then you will know the pressure. And that's how pressure is measured, okay, according to that. So it has to, the gas molecules has to collide with something in order to feel the pressure. So I wanted to have that out of the way, so then you can help me answer this question. So here we have some gas particles. So we have 1 liter container, 1 atmosphere, and I take a piston, which there is a piston here too, and I compress this to half a liter. So now my gas is in here, and do you think the pressure is going to increase or decrease? Increase. Increase. Okay, and it's very logical because you have more particles in a small area, so which means they're bouncing off a lot more with the walls. Are we good with that? Okay, so which means that if you decrease the volume, you increase the pressure. That's what happened, okay? Which means that the relationship is inverse, okay, as we say it. So which means that pressure is inversely proportional to volume. This little alpha symbol here is for proportionality, okay? And so that's how we represent this. And then we say, okay, well, proportionality doesn't do much for us because we don't work with proportionality, we work with equal signs in math, okay? So we need to bring it to an equal. So we say that pressure is equal to, now when you remove a proportionality, you have to add a constant. So any constant, and a constant is a number. It's a numerical value, and we will put that numerical value there sometime. Okay, not right now, we will. So which means that what we are trying to say is that PV is equal to constant. And how does that help us? It helps us because we say that PV, initial conditions, are constant, and this is equal to PV as in final conditions. Okay, so which means over here, 1 liter times 1 atmosphere should give us 1, good? And here, by the time we multiply these two numbers, we should also get 1 because that's the constant, okay? Because by the time you multiply pressure and volume, you should get the same answers, which means that pressure here must be 2 atmospheres, okay? So that's how we relate our pressure and volume, okay? And so your final formula is P1, V1 is equal to P2, V2. So in the final formula, you don't even have that constant anywhere, okay? Although I will bring that constant up later on, okay? So if you want, you can give this A. PV is equal to A, okay? And that's fine, we'll leave it at that because later we do have to give it a numerical value. Are we good so far? And this is Boyle's law, okay? And Boyle's law is also very useful. All of these laws that we are going to learn, they're all going to be very useful practically speaking, okay, as far as pressure and volume is concerned. So for example, if you're driving from here, Florida, which is very much at sea level, okay, in fact, like in another 50 years, I don't even know if it will exist anymore, okay, but pressure here is different. Pressure here is maybe about 1 atmosphere, let's say, okay. So if you're going from here to, say, Denver, okay, and Denver is what, 6,000 feet maybe, 7,000 feet high. So what do you think the air pressure is there, lower or higher? Lower, okay, it's very high above. So there's more gas molecules down here than there, right? So the pressure is lower. So the tires that you have filled up here with air, what do you think is going to happen as you go to Denver? Do you think they will expand or do you think they'll shrink? The pressure is decreasing, so they should expand. Which means by the time you get to Denver, you might want to take out some of that air, okay, from there because they would have expanded. You see what I mean? So it has a really good practical application when you're trying to do all of these things, okay, regarding air because it is prevalent in our world. Okay, do you have a question?
Yeah.
Okay.
Is there any time when you'll be given a situation where you have gas in one and then you compress it and P1V1 equals to P2V2 will be significant, like you can't use it to determine?
There are some conditions like that, okay? Right now when we try to work with these kind of laws, we're assuming a lot of things. Okay, we are, all right? And later on we'll talk about when we don't assume things. Okay, all right, so then let's go on to Charles' law. Charles' law is the relationship between volume and temperature. Okay, don't know if you've ever done this or not, but if there is a birthday party or there's a party and you have gone to the store to get balloons filled up, have you ever done this? You have done this, okay? And they fill it up with helium, okay? So they fill it up with helium and then you walk out of the store and maybe you leave the balloons out for a while or you leave it in your car for a while where it is even more heated. So what happens to the balloon? They pop. Okay, invariably 1 or 2 of them may pop. Okay, so what happened? They expanded. Okay, so what happened? Let's look at that. When you were inside the store, there was a certain temperature, right? And so the balloons were filled to a certain volume. When you came out, the temperature increased in Florida, not in Denver. Okay, but here in Florida at least, they did increase. So if the temperature increased, the volume also increased. Okay, so it's a direct relationship, that's what we say. So you increase the temperature, you increase the volume, okay, of something. So which means that volume and temperature are directly proportional to each other. Okay, so at this point, if you want to remove the proportionality, so V is then constant times T. So let's give this constant B if you want, which means V over T is constant, which means that V1 T1 is equal to V2 over T2, and that is our formula for Charles' law. Whatever I'm boxing here for you, those are the ones that you really need. Okay, and if you have the chapter summaries, again, those are all given to you, okay, but you should know these anyway. So that's Charles' law, and the Charles' law is a relationship between pressure, volume and temperature. One thing I would like to kind of bring to your notice over here, because we've talked about two relationships. One is an inverse relationship. Inverse meaning one thing increases, the other decreases, and the one thing is a direct relationship. Okay, so I want you to see how they are placed actually in the formula, because it's going to help you later on also. So P1, V1, if they're written together, those kind of relationships are inverse relationships. Okay? If they are written like this on top of each other, then they're going to be direct relationships. Okay, so that's something to keep in mind as you go on further. Okay, third law is Avogadro's law. Okay, Avogadro's back. Okay, and Avogadro's law obviously has to do with moles. Okay, and moles is also the number of atoms, which we don't really talk about the number of atoms, okay, as 6.02, but it's still there, okay, times 10 to the power 23. It's still there, but we say that it's a mole. So this is a relationship between volume and N. N here is the number of moles. What we did for you before with moles was actually M-O-L-E-S, right? That was moles, that's the spelling of moles. To cut it short, we took out the E for you. Big deal, right? Okay. And now we make it even shorter, okay, for you. So now we have N for moles. This is something to kind of keep in mind, because M for moles cannot be used because M is a very, very common letter, okay, in chemistry. So N is used here for moles, okay? And so this is a relationship between volume and moles. Very simple relationship here, okay? So if you fill more air in a balloon, what do you think is going to happen to the volume of the balloon? Very simple relationship, right? So which means it is direct or indirect? Direct. Direct relationship, and so therefore V is directly proportional to N. You know where I'm going with this. Okay, it's exactly the same thing as we did for temperature, so which means that V is equal to Cn. C again is going to be my constant over here. Okay, it's a new constant. So which means V over N is equal to constant. So V1 over N1 is equal to V2 over N2, and that is my Avogadro's law. Good so far? All right. Now I want to mention a few things since we have all of this in front of us, okay, right now. One thing that is a common factor in all of these laws is, what are we studying? One of the common things. V, volume. Okay, so that's a common factor in all of these, okay, which tells you that the volume of gas is a very important thing. It can affect the pressure, it can affect everything, okay, in there. So that's one important thing. The other thing that I want to bring to your attention over here before we go too far is in each of these laws, we're only talking about two things. Okay, so here, pressure and volume, volume and temperature, volume and moles. So what happens to the other variables? Just because we're talking about pressure and volume doesn't mean that we don't have an amount of gas. We have an amount of gas, right? We have n number of moles of gas. But the thing over here that we have to keep in mind is that those things are constant. Okay? So you're not changing the number of moles, you're also not changing temperature over here. Okay? So when you study Boyle's law, you keep those two things as constant. Okay? Because the more variables you have, the more confusion you have as to what caused the change, right? So you don't know what caused the change. So in order to study variables, you should do two at a time. So if you change one, you can observe the other. Okay, and then once you know that, then you move on to the next thing. If you have more variables, it causes more confusion. So it means that the other variables here, they are constant. So here temperature and moles is constant, here pressure and moles is constant, and here temperature and pressure is constant. Okay, you're not changing that. So you're just studying the relationship between volume and moles in there. We good? Okay, now what I'm going to do is I'm going to take all of these laws and I'm going to combine them to give you what's called the combined gas law. Okay, so let's see. I'm going to take PV is equal to constant. So this, let me put that as A because that was my first constant. So V is P, A over P. That's the Boyle's law. Charles' law is V is equal to constant times T. And then Avogadro's law is that volume is Cn. So I'm just taking all these laws and I'm writing them together. And now I will combine them, okay, to give you one law, which is then taking all the V's together. So V is equal to, and now I'm going to give it a new constant because I can't use the ABC. If I combine all of these things together, I will have a new constant. I can't use the old ones. Okay, so I'll have a new constant, and T and N are on the top, and P is at the bottom. You good so far? Okay. I'm going to put all of that together. PV over NT is equal to a constant. Just rearranging that equation a little bit. If you're good in math, you're probably in heaven right now. Okay. And so then I can say P1, V1 over N1, T1 is equal to P2, V2 over N2 and T2. And that's the combined gas law.
Earlier I was going to ask if you're asked to calculate all three, Boyle's, Charles, and Avogadro's, you would just use the combined constant.
What I do is I just use this. Okay.
Instead of singularly.
Instead of singularly using these. But however, if you remember them separately also, that's great, because you should know them separately also. Okay. But the thing is that you can see all your laws right here. Okay. You can see Boyle's law right here. Volume and temperature, that is Charles' law. Volume and moles is Avogadro's law. So all the laws are right here. In addition, you can also see the relationship of pressure and moles. So what's the relationship of pressure and moles? Direct or indirect? Direct relationship, because they're on top of each other. Okay, so which makes sense, because if you increase the number of moles of gas, you should also increase the pressure.
So
okay.
The relationship between moles and temperatures also is indirect.
It's indirect then, inverse. Okay, and so you can study other things in there. You can look at other relationships, although you probably will not be asked to, but you can. Okay, when you have everything combined together, you can get a lot more information. Now, regarding the separate laws, as in Boyle's law, Charles' law, Avogadro's law, I would highly suggest that you remember them as three separate ones and at least know what relationships you're studying in them. But when you start solving problems, okay, then this is the best law. okay, to follow, because this is all there all together. When I give this to you on the exam, this is what I give you. I don't give you the 3 laws, okay? So you then figure out which one you need from here, okay? So we'll talk about that as well. But in any case, let's talk about this constant, because we need to talk about this before the day is over today. So PV over NT is equal to a constant, okay? So now we need to come up with a number, okay, of a constant, because we've been avoiding it, okay, so far. We haven't dealt with that at all. And that leads us to what is called the ideal gas law. Oh my God. Yes, we'll be all lawed out today. And so the ideal gas law is when PV and over NT is equal to a constant. We take this and we try to find out what that constant is. So to find out this constant, you need to know the values of pressure, volume, moles, and temperature. Okay, and so what do you use? So you try to use something that is a little bit more standard. Okay, so standard numbers will give you a standard constant. Okay, and a constant again is a number which can be used anytime. So for standard, we say we have what we call STP, and that is standard temperature and pressure. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. Let's talk about temperature for a second, because I should have mentioned that back when we were talking about Charles' law. Temperature is a very unique thing, because temperature, you have, just like pressure also, I guess, so not very unique. You have 3 different units for temperature, right? Celsius, Fahrenheit, and Kelvin, okay? For gas calculations, you will always use Kelvin as your temperature units, okay? And you may want to write that over here maybe. Use Kelvin units only, okay? So that is degrees Celsius plus 273. You will probably never use Fahrenheit, okay, for any calculations, and whatever data you'll be given most likely is going to be in Celsius. So then you will calculate Kelvin from there. So my question to you first is, why do we use Kelvin and not degrees Celsius?
You don't get negative number.
You can get negative number, that's one thing, okay, and you can't have negative answers, okay, in these things, first of all. And the second, it's also on the board. You can't divide by 0. Okay, and if you multiply anything by 0, you get a big fat 0, okay, as well. So you can't have zeros, okay, in there you can't have negative numbers in there. So which means that you have to use Kelvin. So temperature is 273 Kelvin. It's easier to remember 0. Okay, that's why we say 0 degrees Celsius for standard temperature, but you know in the deepest of your heart that it is 273 Kelvin, okay, when we're talking about this. And so the pressure is still 1 atmosphere, no problem there. Okay, so we got 2 values, pressure and temperature. So what about volume and moles? And here's the other 2 values for you. And so we say at 0 degrees Celsius and at 1 atmosphere, okay, 1 mole of gas will occupy 22.4 liters of space.
Where did we pull that number from?
Oh, I don't know. Our hat.
Okay.
No, it's something that you can measure, okay? And we happen to be in this classroom, which happens to have 22.4 liters of gas right here. That is 22.4 liters, okay, right here. So this one will have 1 mole of gas, okay, in there. So at 0 degrees Celsius and at 1 pressure, 1 atmospheric pressure, 1 mole of gas is going to occupy 22.4 liters of space. So once you have all of these things, and I lost my pen somewhere. Here. Now you can plug in all of these numbers into this equation and you can come up with the constant. Okay, and that constant is called the gas constant. The gas constant is R, which is PV over NT, and it turns out to be 0.08206 liters atmosphere mole Kelvin. It has all the 4 units in it because you needed all the 4 units in order to get that number. So that's the value of R. I will give you the constant. However, you will know that eventually you will remember it, just like 6.02 times 10 to the power 23. You don't forget that. You will also not forget this. Okay, there is no way you can forget this. Okay, the value of R is actually dependent on what kind of numbers you use, right? So we used very specific numbers over here. And so if you change any of these numbers, the value of R is going to change. So that is why we use this one. And again, you know that our standard temperature is not 0 degrees Celsius. Okay, we don't exist in 0 degrees Celsius. But you have to make certain assumptions, otherwise you will not be able to work. Okay, so yeah. Okay, not a real gas.
When
okay?
would you use the ideal gas law?
So let's wait.
Okay.
Okay, all right. Yes.
22.4 divided by 273 is 0.08205 on my calculator.
So 0.5, just a little bit different. And actually, you tend to use 0.0821 for most part.
Okay.
Okay, yeah. So yeah, it'll come out to be approximately the same. Okay, and yeah, there was a lab also that we used to have for this one, but the number was never coming out right. Okay, and also maybe also because our temperature is different. You know. Yes, come.
Absolute zero is 273.15 Kelvin.
Maybe that's what was making the difference. Because maybe the 0.15 could be. Yeah, because we don't use the 0.15 so regularly, but it is there. That's true. 0 degrees Celsius is 273.15.
Yep, that's the difference.
That is the difference?
Uh-huh.
Okay, all right. So yeah, that could be making the difference then. Perfect. Okay, so we got that out. So here the ideal gas law then, the way we write the ideal gas law is not quite like this. We write it like this. PV is equal to nRT. And please box that and keep that forever somewhere in your heart and your mind. So PV is equal to nRT. R here is the gas constant. Okay. On the website, my website is maybe on the blackboard also. I'm not quite sure. Okay, but there is a little video that I posted. It's a YouTube video, and if you have 5 minutes to kill, go ahead and look at it. It's a nice rap song. Language is bad, little bit, okay, but look at that video, it has all the gas laws in it. Okay. So in any case, the gas law here, this is an ideal gas law, an ideal gas law meaning if everything is perfect, okay, that's when you have ideal. When you have real gases, okay, or when you have real situations, then things are slightly different, okay? You have to make certain assumptions with gases, okay, because they're not going to behave properly. Gases are just like people. People don't behave, okay, properly either. And so therefore, you know, gases also don't behave because they're also very sensitive, just like people. And so therefore, you know, this is what we will call an ideal situation. That's all it is we can say, okay? Later on, as we get towards the end of the chapter, I'll probably talk just a little bit about what real gases are like. Okay, because this is for only ideal gases.